Welcome here. Today I will try to simulate an 3-point bending test for a concrete beam sections, and our target is to produce a load versus displacement graph like this. So we'll try to simulate this today. So I will start the procedure. First of all, we'll have to define the part sections. The part sections are already defined. There are mainly three parts, that is support parts, crack parts and beam parts. The crack parts is redundant because we will actually use an crack propagation model like X-frame, which will automatically determine the position of the crack. So we will delete these sections. We do not need it today. But if anyone wants, they can also use the crack point to navigate the crack starting point. So the beam sections now actually consist of these two parts. This is beam and this support. We'll use materials, concrete materials. The material is defined as follows. The Young modulus is 30,000, Poisson ratio 0.2. Density is 2.4 e to the power minus 9. Maximum stress is 3. Damage evolution, in which we use type energy type and fracture energy 0.1. And damage stabilization coefficient is 5 e to the power minus 5. Okay. So this is the material we have defined. We will use it, and that we will create a sections. And how to create a section, that is we'll click solid homogeneous and then create in sections, and we'll assign a material in these sections. So we have created a sections. Similarly, we'll create this section. I will delete my part, so I will create in these sections, and I have assigned concrete actually. Now we have to assign these sections to in that part. So how we'll do that? First of all, we'll go to the assigned segment, then sections, and we'll click the part that in which we want to assign the section. So I'll click this part actually. So I will click done. So this is already defined, so we do not need to do that. Now we'll go to the assembly sections. So the assembly is already done. There are assemblies look like this. There are two support cells. These are two support cells. The beam is, this is the beam, this is supported by it, and there is a load cell in the middle of the beam actually. So this is the assembly looks like actually. So I will skip the assembly part because anyone can easily assemble the parts in the abacus. Okay, fine. So next step is to go to the step section. So we will create a new steps, that is we will name it step 1, that it will be static and general. Continue. We will on this module because it will include the effect of nonlinearity. Then we will go to the incrementation segments. We will use increment size of 0.2. Maximum fracture of increments we will use 10,000 to 1 lakh. I will prefer 1 lakh for smooth simulation results. I will use maximum increment size of 0.5, and minimum I will use 1 e to the power minus 15 actually. So this is the segment. After doing the step parts, we will go to the two other sections and go to the general contour sections, then manager sections. I will click step 1 and go to edit sections. Continue. I will go to the specify options. Then I will click on time incrementations. I will input the value of IO equal to 8 and IR equal to 10. Then I will click on the more options. Then I will assign the I equal to 15. The I value is the number of failure value before the simulation stops. So the simulation abacus will try 15 times before exiting the simulation with an error. Okay. So I'll click OK. Now for the field output request, I will go to the field output request. Before go to the field output request, actually I will go to the interactions. I will double click it and then click initial, then general contact standard. I will select this all with self, then I will click this part. I will click contact, mechanical tangential behavior, penalty, friction coefficient is 0.1, then mechanical normal behavior. This is all good. I will click OK, then OK. So I will click in this part. I will try to find the contact pair in this segment, so I'll click find contact pairs. So there are 3 contacts in this assembly. The first is between the beam and the support. Then this is the load cell with beam actually. So I will click OK. Now I will go to the special segments, then crack, then create. I will click XFrame. I will use crack 1. I will use crack 2 or whatever it is. I will use crack 2. Okay, I will select the domain for crack and I will click OK. Now I will go to the interactions, click create, and I will click step 1. Initial, then XFrame crack code, continue. I have created a crack of crack 2 XFrame crack module and click OK. So our interactions module is good enough. Then we will go to the boundary condition modules. So first of all is symmetric anti-symmetric encasted boundary condition 1, continue. I will select this point, done. Then I will encastate it. Similarly, I will create another boundary condition, mechanical, symmetric and step initial, continue. Then I will select this point and I will click done. So I will also encastate it. Next, I will create another boundary conditions. This time it will be displacement and rotation in step initial, continue. I will pick this reference point, then done. So I will click these parts. Okay. So okay. Now I will create another boundary condition. This time step will be step 1. Continue. I will click this reference point. I will tick these things, and in the U2 segment I will input -20 because I want to displace the load cell in the y direction, in the negative y direction, -20 millimeters. So I have inputted U2. If I assemble the beam in the x direction, then I should inputted -10 or minus similar things actually. So I will input -20 because I want to displace it in the negative y direction. So I will click OK now. Okay, fine. So now we'll go to the field output request. So in this field output 1, I will click it, and then we'll go to the state field user type. Then we'll click load XFrame, status XFrame and status, and we'll also go to the failure and fracture. Then we'll click this on and this on. Okay, fine. So I will click now OK. Now I will go to tools, set, create. I'll create a set, name reference point. Okay, actually, so continue. I will select this reference point for these things, done. Now I'll go to the history output request, and I will create an history output. These two, continue. I will select set, then select my created reference point. I will go to the force segment, that is the force segment. I will tick it all, and then I will go to the volume and displacement. So I will click these parts actually. Okay, fine. Okay, so now we have created two history output requests actually. So this is done. Now we'll go to the mesh sections. How will we mesh it? First we'll click part segment, then beam, then we'll select these parts. Then I will click this and mesh it. Similarly, I will go to the support sections. I will select it. Then mesh part, mesh. So mesh has been done. Now I'll go to the job module from this. So I'll go to the job module. I will create a new job. Names concrete. beam simulation. Fine. So I'll go to the parallelization part. If you have multi-core processor, then you can uh, increase the value of the processor that will be used in the simulation. I have 4-core processor, so I have inputted 4 to accelerate the simulation. Okay. So I'll click OK. Now I'll go to the sections and I will submit it. So there is a crack defined actually. So I will go to the interaction parts. Then I'll go crack, then manager. I'll delete this crack because it is getting error. Crack 2 is fine enough. So now we'll again try to, now we'll create another one because this file is already finished. So I'll get job, create in concrete. I'll go to the parallelism. Okay. So now I'll create submit. So the simulation has been submitted. Let's see if it runs or not. So the simulation is running. You can see that it is running actually. We will wait for some time. Then I will pause the video to finish the simulations. So it is running. Actually, you can see that it is finding the solutions. Okay, so it is trying to find the solutions. So we can also go to the result segment, the result which is already been produced. We can see that there is already a crack in these segments. So it is the load segments. The simulation has not been completed. It will run for some times. I will pause that video for that moment actually. Thanks. So our simulation has been completed. Now I'll click it and go to the result segments. Now I will go to this and use these parts and click it. We can see the four segments. Now I want to see the crack propagation, so I will click it these things and I will focus in it. I will try to slow it down. So we can see the stress concentration actually. And also click in this module. This is the stress segment, how much stress is produced in each case. Now we'll try to create the graph, load basis time graph that we are trying to create. So I'll click accept create data, whatever history output, continue. Then I will select reaction force RF on, then plot it. Okay. So this is the reaction force and this is the energy whole model actually. I will go to the file. So this is our actually our task and this is our model actually. So this is the A model, this is the A model, and this is the sudden load and displacement time. Load displacement. This will graphs will match the amount match of the description of the picture because we have used displacements of -10, but if we change the value, in this case in boundary 4, if you use -20 or -30, it will create similar types of results actually -30. Then we'll try to simulate it again. So this was done actually. So this is the load basis time graph we have been produced using 3-point bending test and back propagations of the cell. So that will be all for today. Thank you all.